AP Chem. Time for your Unit 4 review now. Aren't you excited? You're like almost halfway there. To, you're halfway there to the hardest unit, acids and bases. Anyway, so this one you're learning about chemical reactions, aka Unit 4. Now let's get started, shall we? So the first one, uh, introductions for reactions. This one is basically saying, okay, can you tell whether a chemical reaction is happening? There are a couple ways to do that. Uh, Most often, what you'll see is stuff like a color change, right? Where like it'll be red and then it'll turn pink or blue, right? Another way is by evolution of a gas. Like if you just randomly start seeing bubbles in your beaker, that's a good way to tell that a chemical change is occurring. If you smell something, aka an odor, that's a good one. That's a good one. Uh, and these are all, and like I'm gonna give you an example that you may not have heard of. If y'all have ever cooked like an egg or something, right? Or if you've like at least watched a cooking video, you'll see the color change. Most often from like clear to white or green, right? You'll see a gas evolve as water is being pressed out of the food, and you'll often hear an odor being described like, "Oh my God, it's so fragrant," you know? That is what is called a chemical reaction. Now, obviously, there are other examples of a chemical reaction, but the but cooking is an excellent example of a chemical reaction, and you can actually have it be analogous to it, right? And this, while it's not going to be necessarily on your AP test, it will be an excellent tool for you to differentiate chemical reactions from physical changes. All right. Now let's move on. Net ionic equations. Net ionic equations are basically reaction equations, right? So, as an example, I'll say ax3 plus bx2 is equal, not equal, turns into cx4, we'll say, right? And these are all ionic compounds, okay? So what this will say, right? If we break it up, all of these are water soluble, right? Actually, to demonstrate it, we'll say Bx2 is solid. And you'll notice that I'm writing these phases here, right? This represents solid. This represents liquid. This represents gaseous. And this represents in solution. AQ for aqueous. They aren't technically recommended by AP, but I would highly recommend you to know these, okay? And it's really simple to remember them, right? It's just like the first letter. Or in solutions case, you have to remember aqueous solution, which isn't that hard to remember given that most solutions are water based or aqueous. That's actually where we get the word aqueous. Anyway, so all of these aqueous ionic compounds we can break down into ions, right? If we have, since this will be a -1 ion, we'll say that A is +3. 3x minus Bx2, solid, stays the same. C4 plus X minus, right? And now you cancel what you can, okay? So for example, I can cancel this such that I get an X minus, okay? And all we're left here is A3 plus BX2 turns into C4 plus X minus. And you can see that I have balanced the equation. This is another concept that we will cover later. In this side, right, you'll see a charge on the A3 plus. And on this side, you'll see a charge on C 4 plus and a charge on the X negative 1. These two add together to become, 3 plus. This is what a net ionic equation is. And actually, you've already dealt with these in Unit 1. If you remember in your lab, you were asked to write a net ionic equation for the silver. A lot of you have actually come to me for that. Silver chloride actually, is usually formed from silver nitrate, AgNO3, and sodium chloride. If we write the equation to that, the just Blanc equation, that's what I call it anyway, we get silver chloride and we get sodium nitrate. We can write the states, AQ for aqueous, S for solid, and aqueous solution once again. And now we can break this up into ions, right? This is called the total equation. Total equation. Alright? And then this will be the total ionic. Ionic, if this will work with me. So we have silver plus, along with nitrate minus, NO3 minus, plus sodium plus, chloride minus, turns into silver chloride, which since it can't be dissolved, we can count that as just one unit. And sodium plus and nitrate. And then we can cancel. Since sodium and nitrate are on both sides of the equation, they're considered non-relevant or spectator ions. So in an FRQ, you might be asked, what are the spectator ions in this reaction? You would say sodium and nitrate since they're on both sides. These are called spectator ions. And this, from here, we can get a net ionic equation. Remember, net, if you don't know, means if you've heard of net income, that means the total amount of income that you have minus taxes and expenses, right? That's what this is. It's the total amount minus your spectator ions. So what the net ionic equation for this would be silver plus, Ag plus chlorine minus, or chloride, turns into silver chloride, AgCl. And notice how it didn't cancel these two ions out. And that is because they have no counterparts over here. You can actually kind of think about it. All of these have an implicit 1. if we turn that into an explicit one, we can actually write silver and chlorine over here. However, the however they have 0, sort of like that. And so when you try and cancel them, one, uh, 1 minus 0 is 1, and so that's over here. 1 minus 0 is 1, so that's over here. And that's actually how you get net ionic. You basically subtract these, right? And again, silver chloride doesn't have a counterpart over here. If we were to write silver chloride over here, we could write it plus 0 AgCl. I'm assuming you guys have taken that level of math before, such that you can do this and the equality has been maintained. And so this is usually the steps that you can get to write a net ionic equation. And actually, once you get good enough at it, you can actually just skip straight to the net ionic. Let me give you an example here. Calcium sulfate is depicted as insoluble. So if we have calcium nitrate, CaNO3 2, and ammonium sulfate, NH4 2SO4. This turns into calcium sulfate, as CaSO4, and 2 ammonium nitrate. I don't know why I wrote the 4 like that. All right. Now, what I will often do is I will separate these in my head. Oftentimes it'll help that you write the states. AQ, AQ, S, AQ. And these are your states. You can separate these into ions, cancel the redundant ions like nitrate and ammonium, and you get Ca2 plus, calcium 2 plus sulfate SO4 2 minus turns into calcium sulfate. Very simple. Very simple, at least in my opinion. If you need help, you can leave a comment. Alright, now on to 4.3, representations of reactions. For this one, I'm going to draw a beaker. I need it to be that big. So, for this beaker, we shall say that red is sodium, Na+. We shall say that orange is Ag+, green is chlorine minus, and blue is nitrate, NO3 minus. So you can probably tell which equation this is, but just in case, I'll write it out for you. This is classic precipitation of silver chloride, which requires silver nitrate, orange and blue, and sodium chloride, red and green. This turns into silver chloride and sodium nitrate. So, we can actually so if we assume that all of these, we'll say, has 4 circles. So 1, 2, 3, 4, and the beaker is obviously filled with solution, right? We can assume that silver plus also has 4. 1, 2, 3, 4. Chlorine minus has 4. And I'm going to draw this in a special way, sort of like that. And nitrate will also have 4. 1, 2, 3, 4. And this is what is known as a particulate diagram. You will see this term a lot in your AP FRQs. And what it means is that you have drawn the reaction as particles. Now, what does that mean? It means that all of these particles represent reactants and products. So if we go back here, this is sodium Na+, this is AgCl, and this is NO3-. And so now you can see that I've represented this reaction, right? And since this is the unit of AgCl, I can make it such that these two are bonded together and they sink to the bottom as a precipitate. Sort of like this. Alright? And at that point, I can kind of just get rid of the AgCl. At that point, I can just kind of get rid of the AgCl in the diagram. And that is because I have drawn it as a precipitate. And since I have drawn it as a precipitate, there is no need for AgCl floating in solution. Now, obviously, this is incredibly oversimplified, and you'll learn why it is oversimplified in another unit. However, this is what is called a particulate diagram, and it's a generally good idea to draw them for the FRQs that require drawing them. It's generally a good idea to also recognize how to draw them. So you might want to train on some progress checks that your teacher has assigned you. And you'll generally want to also look at some examples. AP Classroom has some really great ones. And that will be our 4.3 review. On to 4.4, represent physical and chemical changes. So physical changes, right? Let's go ahead and do a little T chart over here, okay? I'm gonna put this for P and C, okay? Physical changes often don't change identity. No identity change. ID change, basically. Chemical change often does have an identity change. So if you think about it, right? Water, H2O, solid, melts into water liquid. Has there been a chemical change? Not chemical change. Has there been an identification change? No, because it's still water. It just melted from ice to water. So that would be melting under here. Likewise, if you have H2O as a liquid and it turns into a gas, this also we can ask the same question. Has there been an identity change? And the answer will still be no, right? Because all it's done is change phases. There's been no real identity change here. And so we can also put boiling over here. On the other hand, you can list some chemical changes. Some simple examples include the Haber process. Nitrogen gas plus 3 hydrogen gas turns into 2 ammonia molecules. And we can ask the same question, has there been an identity change? And the answer is yes here, because we have nitrogen gas and hydrogen gas turning into a completely different compound, ammonia. And I want to stop here for just a second. We took a we took two completely different molecules, smashed them together, and created an entirely new molecule out of that. This is called synthesis. We can all the other chemical reactions uh, also fall into this category. We'll go over them later. And if you want, and now it's time for a little bit of a confusing one. Let me show you. Sodium hydroxide, NaOH. This is used as a drain cleaner. You can pour it down your drain and it will often dissolve all of the things that is clogging it and making it go faster, right? It dissolves in water. Has a chemical change occurred? This and again we can ask the same question. Has an identity change occurred? The answer would be yes, right? Because sodium hydroxide turns into sodium ions and hydroxide ions. However, if you boil off the water, you're left with sodium hydroxide again. So this is where it gets complicated. Oftentimes what you'll see is dissolution be placed in the chemical reaction side. All right? And I wanted to bring this to your attention as some of you may classify this as a physical reaction when AP really doesn't want that. It will vehemently say, no, that is not correct. Okay? And so, this will be a chemical change. Okay? So, as a little bit of a sub review, physical changes are changes in which there has been no identity change. Chemical changes are those where there has been an identity change. And you can actually see that in our analogy of cooking. So, say you have an egg, right? I'm just gonna draw one sort of like, you know. If you have an egg, right? You know, and if you cooked one before, you know that the egg white starts to turn white, and the yolk starts to turn yellow. What this is a chemical change, right? However, if you ha- however, if you take the same pan and you put an ice cube on it, you can say that the ice cube will melt and then the resulting water will boil. Though that is a physical change. And now let's move on to stoichiometry. Stoichiometry. Personally, it's one of my favorite subunits. Sorry. Stoichiometry is all about balancing reactions. What it is, it's basically just seeing what coefficients can go with the molecules such that all the atoms in the molecules are equal. All the atoms have been used, right? And this comes down to a physics principle called conservation of mass. And if you haven't heard of it, I highly suggest you go ahead and do so. I'm just gonna go ahead and give you like the like textbook Control C Control V answer. Conservation of mass is mass cannot be created or destroyed and can only be transferred. A good example of this is you can't. A simplification of it is you can't create mass and you can't destroy mass. Mass will always be existent and it will always have some value. Basically, mass of the universe is constant. For chemistry principles, we can say that. Physics nerds in the comments can flame me about that. I don't care. Uh, what will happen, right, is uh, if you have an unbalanced equation, you need to rebalance it such that nothing happens to the mass. Because otherwise, you have broken a physical law of nature, which AP doesn't like, per se. They really don't like that. They really, really don't like that. So, the main tenet of this is going to be redox reactions. These are hefty. So, right here, you can see I've drawn dichromate. Additionally, here's manganate. Permanganate, sorry. These can be balanced in several different ways. If it's an acidic solution, it will form chromium 3 plus. If it's in neutral or basic solution, it will form chromium 3 hydroxide. And if it's in super basic condition, almost never it will almost never do this on the AP test, but I thought I'd tell you anyway. It will form chromium 3 hydroxide minus, which is insane to think about. Something similar will happen with permanganate. Notice how I emphasize per. In acidic solution, it will turn into manganese 2 plus. In neutral or slightly basic solution, it will turn into manganese 2 hydroxide. In super basic conditions, again, almost never, it will turn into manganate, a green ion instead of a purple ion, which is also insane to think about because the pH levels to do that are insane. You have to get like pHs of 13 or 14. So, what all does this mean? And let me tell you. This all comes down to a principle known as oxidation states. So if we have redox really comes from the words reduction, oxidation. Paint doesn't like MS Paint doesn't like me going so fast. So these two words have been simplified down to redox. And this all comes down to oxidation states. Let me give you an example. Oxidation states, usually if they're monatomic ions, aka one atom ions, match the match the charge. So if you have a silver plus ion, then the oxidation state of that is +1. If you have a chlorine minus ion, then the oxidation state is -1. If you have an iron 3 plus ion, then the oxidation state is +3 or 3 plus. And so on and so forth, right? All the monatomic ions will follow this rule. And this is all for monatomic. But not everything. if it's a polyatomic molecule, then then we need to make a couple more tweaks. Usually halogens, X in this case, will have a -1 oxidation state. Oxygen will have usually a -2 oxidation state, except in fluorine where it can have whatever because of electronegativity. Nitrogen will have -3. Hydrogen, usually +1. And so now you can sort of solve like oxidation state problems. What the oxidation state problem will be, I don't know. For an example, I do know. Uh, oh yeah, sorry. Polyatomic molecules or ions, all in addition to these ones, the oxidation states, the sum of the oxidation states. So I'm going to put a Greek letter, capital letter sigma here. The sum of all the oxidation states will equal the charge. Always. And so, let me give you an example. Sulfate, SO4 2 minus. So we can apply the same rules here. SO4, O4, 4 times -2, and that is -8. The total oxidation state is -2. And so for sulfate, we can do -2 minus -8, which is equal to 6, plus 6. And you can do this for every single polyatomic atom or ion there is. Every single one. And these rules will hold for all of them. So now let's get to the actual meat and potatoes of this. Okay? So now we're going to bounce redox reactions. So redox reactions are essentially reactions where if A plus B turns into C plus D, then A has lost electrons, or gained electrons, and B has gained electrons. Since A has lost, then B has gained. You can actually and this is really freaking confusing. Reduction is gain of electrons, and oxidation is loss of electrons. A couple of you can actually remember this using a couple mnemonics. Sorry. Most famously, oil rig and Leo the lion goes grr. G-E-R. E-R. So this stands for oxidation is loss, reduction is gain. And this is essentially the same. Loss of electrons is oxidation, that's Leo. Grr is gain of electrons is reduction. They're stupid, but they work. I have used these mnemonics for so long, and they have never failed me. So let's do a couple of examples, shall we? So let's do a couple of simple examples first, and then we'll work our way up to more complicated ones. So silver, Ag, and zinc 2 plus will turns into silver plus and zinc. Obviously, I'm not taking thermodynamic favorability into account. We don't get into that until Unit 9. So, silver loses 1 electron. We can actually write this as as what we call a half reaction. So what this is a half reaction is representing just that element, okay? Or just that compound. A half reaction basically writes out the reduction or the oxidation. And E minus here represents an electron. And then we can do the exact same thing here. Zn2 plus 2E minus. E minus, paint really hates that I'm going fast, turns into Zn. And here, since we don't have any electrons in any redox equation, we have to balance it. So we can multiply this above reaction by 2 and then add them together. The 2 electrons cancel, nothing else does, so we have 2Ag plus Zn2 plus turns into 2Ag plus Zn. Alright? And so that's going to be a very simple example. It's also going to be probably one of the least prevalent on the AP test. I'm sorry. They do still occur though, which is really nice when your brain's hurting. So what you'll often see is one of these two. For sake of argument, let's go permanganate, MnO4 minus. Permanganate, and we'll say silver plus. Yeah, silver plus. Turns in, wait no, silver, sorry. Silver plus, and again, for the sake of argument, we'll say that it's an acidic solution, and so it turns into Mn2 plus. Let's go. Ag turns into Ag plus and an electron. MnO4 turns into Mn2 plus. And you may be wondering, where did the oxygen go? The oxygen escaped in the form of water, H2O. And if you're wondering where did the hydrogen come from, that's where the acidic solution comes in. Since this has 4 waters, we need 8 hydrogen ions to completely neutralize the water. Now you may be noticing the charge isn't balanced. And so what we have to do is we have to add 5 negative charges or electrons to this side to make it completely balanced. And now we can add the equations together. Uh, since there are no electrons in any ionic redox equation, we have to multiply both sides by 5, cancel the electrons, and we have 8H plus 5Ag plus MnO4 plus turns into Mn2 plus 4H2O plus 5Ag plus. This is pain. I wish that there was a shortcut to do this, but there isn't. Let me just... Okay. So, for future reference, here are the steps to doing the half reactions. So number 1, you break the reaction up. Break it up. As the name suggests, you break it up into 2 half reactions. The oxidation half and the reduction half. Number 2 is you balance both of the other equations. So balance atoms, aka mass, and crucially balance charge using electrons. And so this actually has a bunch of subsets to it. You balance electrons by finding the least common multiple between both of them. In acidic solution, you can actually get away by skipping this step and doing it at the end. In basic solution, you really can't. Uh, in acidic solution, you would add water for oxygen. In basic solution, you would have OH minus for O. For O. You balance, and then finally you balance the hydrogens. This by adding H plus or H2O. This is then followed up by adding the two equations. And this is the general steps for how to balance a redox reaction. And now, without further ado, we are done with redox. And we still have one more section to go. Types of chemical reactions. There are 4 main types. If you've already taken advanced chemistry, you do not need to watch this part. However, for those who have skipped that, here are those 4. Synthesis, in which A plus B turns into C. You have decomposition, in which C turns into B plus A. You have single replacement, in which A plus BX turns into AX plus B. And you have double replacement, which is AX plus BY. BY turns into AY plus BX. These are all the equations that AP wants you to know. And as an example, we'll start with synthesis, the Haber process, which makes ammonia, N2 plus H2, 3H2, turns into 2H and H3. You have decomposition, which is many explosives. You don't need to know this one as well. For ammonium is going to be a very good explosive. Single replacement can be done with zinc and silver. So if you have zinc and silver nitrate solution, AgNO3, you can turn that into silver and zinc nitrate solution. And for double replacement, you can just do what we've been doing. AgNO3 plus sodium chloride turns into silver chloride and sodium nitrate, NaNO3. That is all for Unit 4. I wish you good luck on your exam, good luck on your test, and as always, ace your exam, get a 5 on your AP. Good luck.